Good afternoon, everyone. My name's Alan Nair. Alongside me we have Colin Hines, Ryan Flynn and Nisha Quinn. Also in our group is Niall Murphy, who can't be here due to unforeseen circumstances. Our group is called Slice Span, and this is our IDP Integrated Design Project presentation. So, at the start of the semester, we were tasked with becoming civil engineers for a particular building in the Limerick Opera development. To do this, we became many different types of engineers, including structural engineers, geotechnical engineers, transport engineers, as well as PSDPs, or project supervisors, to the design process to design numerous elements of our building. So taking a closer look at the Limerick Opera development, this is a project being completed in conjunction with the Limerick 2030 project. As a project that Limerick 2030 says wants to be recognised internationally as an example of designing the most innovative region, reinventing Limerick as a vibrant, modern and dynamic place. The building is situated in the centre of Limerick City, just south of the River Shannon. It is 3.7 acres of land, and at completion it is expected to have the capacity to employ 3,000 people. Taking a look at our building in question, which you can see here, is a first floor plan view of the building. It has an accommodation space of just over 15,000 square metres. This encompasses retail space, restaurant and cafe space, as well, but mainly office space, which you can see here for the first floor plan. It's all office space, which is 13,000 square metres of the building. As I said at the start of the year, we became different types of engineers. This included surveyors. So in October, we set out to complete a topographical survey of the site, of the area around our site of our particular building, as we weren't allowed on site. This included taking points of features along Ellen Street and Michael Street. After completing that, we were able to upload these points into our computers, and using our CAD skills that we garnered over the semester, we were able to complete a survey drawing of our site, of the area around our site, which you can see here. I will now allow Niall, who has recorded his slides, to talk about the planning elements of our project. Can you hear that? No. So I'll just go back.
Due to the size of the project, we came together at the beginning of the semester to create a project programme of every task that must be completed. This gave us a way of organising ourselves in meetings by giving us a structured plan to follow, an ability to track progress, highlight deadlines that need to be met, and identify a critical path to the completion of the project. The critical path included health and safety report and a mobility management plan, RC slab, beam and column reports, geotechnical report, and a poster for the horizontal load pass. One of the first tasks identified from the project programme was a health and safety report, which consisted of a designer's risk assessment. As designers, it is our responsibility to assess and control any potential hazards and communicate controls to the relevant teams. Hazards are scored using a likelihood versus severity matrix. Controls are then introduced to eliminate or reduce the hazard. An example of this is to specify the use of tempered glass over normal glass to reduce the risk of glass breakage. One of Limerick City Council's policies is that any developments that will produce significant trip generation and attraction rates must require a mobility management plan. The main aim of our mobility management plan was to utilise existing travel facilities in the city. An example of this shown on the right here is the Coca-Cola bike sharing scheme, with stations located within a minute's walk of the development. We also introduced measures to encourage sustainable travel. This included a mixture of hard and soft measures, such as a hard measure of having a safe and secure bike storing facility in the underground car park of Parcel 1, and a soft measure of organising a weekly bike mechanic visit for all employees. A subsequent road safety audit was also carried out to identify any as around the site, such as cracked footpaths and no road marking, and suggest a suitable solution for these problems.
And now passing on to Colin, who will talk about the load paths.
When deciding what our floor layout would look like, we had to consider how this layout would transfer A, the vertical loads, and B, the lateral loads acting on the building to ground. This is a floor plan of the first floor of Parcel 1. The floor layout we chose used slabs spanning from left to right in the orientation shown here, which spanned onto the beams shown in red here. The beams then spanned onto the columns shown in yellow, which acted an axial compression to transfer the load vertically into the foundations of the building. We chose to orientate our beams, slabs and columns in this way as we felt it tied in well with the architect's existing drawings and provided the most economical spans for our slabs and beams. Next, we had to consider if this structure would provide stability when loaded laterally under the wind load. The frame of Parcel 1 was determined to be a braced frame, meaning that all lateral loads were resisted by shear walls or other forms of bracing, which could transfer horizontal loads into the foundations of the building. When the wind blows on the face of a typical window of Parcel 1, as shown on the left, it sends the window into bending. The window is then supported on either side by a mullion, which also experiences bending due to the load on it. The mullion is supported at either end by the edge beams of the building, meaning that the point load reactions from the mullions load the beam uniformly along its length. This beam then loads the edge of the floor slab of the building. As the slab is loaded in a stiff plane, it acts as a rigid body to transfer load through what is called diaphragm action. The load is then transferred via diaphragm action into the shear walls of the stair core and lift shafts of the building. The shear force creates an overturning moment at the base of the stair core. This is then resisted by a restoring moment at the foundation. The load transfer to ground is now complete. I'll now pass you on to Ryan, who will discuss the reinforced concrete design of the key structural elements of our building.
Thank you. So at the start of our design, we had to consider different slab types, which included the one-way spanning slab, the rib slab, and the two-way spanning slab. However, we decided that for our design, the one-way spanning slab was the most appropriate. We felt this because it is simple and fast to construct. Holes in the slab will cause few structural problems, and it can be economical for spans of 4 to 7 metres. We also believed that this slab design would allow us to complete a more comprehensive analysis due to its simple design. Each member in the group took different sections of slab within the building layout, and they designed these slabs by taking a design strip of 1 metre wide to size the reinforcement and then check the suitability of the section. Initially, to size our slabs, we used span to depth ratio tables from the Concrete Building Scheme Design Manual for reference to Eurocode 2. Looking at a multiple span for one-way spanning slab with an imposed load of 2.5 kilonewtons per metre squared, which we chose for office space use. Looking at that with a typical 7.5 metre span within our building, using that factor we get an estimated depth of 240 millimetres for our slab. Some of the checks we undertook when designing our slab were bending, which was done during the flexural design to size the reinforcement due to the implied moments, shear and deflection. Bending and shear forces were generated using coefficients with reference to Eurocode 2, which we developed allowed us to generate bending and shear envelopes. Our final design then, we chose a span for the slab of 7.5 metres, a depth of 235 millimetres. The reinforcement was H12 bars at 125 millimetre centres, and we also found that this section was the most efficient in resisting shear. Moving on then to the beam, we decided to choose a beam that we felt represented the general beam arrangement within our floor, and for the analysis we chose the 7 and 9 metre critical spans for the design. We used the Limpro software analysis to design our beams by inputting loads and load combinations to determine bending and shear force diagrams to help us do our analysis. We consider 3 load cases, min-max, max-min, and all-max, to allow us to find the largest bending at in the critical points of our beams, which you can see here. For each load case, we chose the highest value of bending moment, which allowed us to generate a bending moment envelope to allow us to size the reinforcement in both the tension, in all the tension zones of the beam. And as you can see here, if we take sections through the top and bottom tension zones of the beam, the reinforcement is sized in all sections with the number of bars and bar sizes listed beside them. We also found that a 600 by 600 beam was most suitable for this design. Sticking with that beam then, when we designed our columns, we again used Limpro, and using the same beam analysis, we included the columns above and below to show that how the moments were transferred into the columns, and this which you can see here on the left hand side. And then we used this to analyze our columns, and from this we then chose the effective length. We chose this by assuming that our columns are fixed on both ends, as it is a brace frame structure. We just had to check the slenderness of the column, check whether it was slender or short, and we found that all our columns were short. We calculated the design moment based on the moments we obtained from Limpro, and using that, hence, we sized our area steel and reinforcement using a column design chart, which you can see here. Our findings then, our final design was a 400 by 400 square column with a 5 H32 bars for the reinforcement. I'll now pass you on to Nisha, who's going to talk about how our building is supported.
So how is our building supported? Our building is supported through the foundation of the structure. Our job is to find the layout and dimensions of the foundation, as well as the loads being applied to the foundation, and how much this overall structure will settle by, and if this settlement will cause any damage to the structure. To figure all this out, we need to calculate the bearing capacity of the soil, the loads being applied, as well as the coefficient of volume compressibility of the soil. So how did we find these values? So we first had to determine whether the soil acted in a drained or an undrained manner. From here then we applied the corresponding tests. So the tests that were carried out were the shear box test and the triaxial test. From this then we were able to calculate the shear strength of the soil. We were also given the site investigation report, which included the boreholes on our structure. The boreholes examined were boreholes 10, 11 and 17. From this then we were able to determine which stress analysis, so a total stress analysis or an effective stress analysis, which one was necessary, and if not, both. So for the settlement we carried out an odometer test, which allowed us to find certain properties of the soil, such as its voids ratio. From here then we were able to graph these results and therefore calculate the MV value of the soil, or the coefficient of volume compressibility. From all this then, knowing all this information, we were able to calculate the overall settlement of the structure. So for our final design, it was decided it would best to remove the clay layer underneath the foundation and replace it with a more granular material, as this would prevent any differential settlement from occurring, which could have induced cracking in the overall structure. We found the foundation size to be 35 metres by 97 metres with a depth of 1 metre, and we found the overall settlement to be 40 millimetres. I'll now pass you back to Alan, who will conclude the presentation.
Thanks, Nisha. So that concludes our presentation. We still have to complete a reinforcement concrete schedule, bar schedule, and a drawing of our beam, which will be completed in the next 2 weeks. As engineers, it's important to reflect and evaluate after a project. So what did we learn? Well, we learned how to design numerous elements of a reinforced concrete, including slabs and columns. We were able to compare them and then choose the most efficient and best element for our structure. We also completed a soils report to determine the foundation of our building. But one of the biggest things we learned for from this project was just how many different types of engineers there are in one specific project. So this, when working with so many people, it requires good teamwork and communication skills. And from this project, we feel that in our group meetings, as well as collaborating with each other, we were able to increase these skills for our future careers, as well as our placement in general. Thanks for listening.